Alright, this time I'll talk about the problem Stringsobit. So in this problem, it's quite a complicated bit manipulation. You cannot just convert this to a string and test out each possibilities. Instead, since they're only represented by 0 or 1, this can be converted into a binary number, and you can use an integer loop to check the possibilities. And so here there are quite a few complicated parts involving bit manipulation, so I added a few side notes to it. And so first I will receive the input. You have to use long for this I because it can get pretty big, the size of the whole set. And so first I have a base case here, just in case if I is equal to 1, then the answer would just be 0. So basically, if for anything, for any length L, and as long as I is equal to 1, the first answer will always be 0. And otherwise, we will use this whole loop to find the answer. First, outside here, I created another long variable called CNT. So this will count how many of the numbers we've already searched through. As I said, 1 is definitely, so 0 is definitely one of the correct answers, so I will set this to 1 at first because that will mean I've already counted at 0, and then we'll start at 1. And here's this is a bit manipulation. You have to use this right shift. So right shift, it's basically the same thing. So 1 to the 1 right shift anything is same thing to 2 to the power of this. And although I can just use 2 to the power of n, I decided to write this because I think it's more clear for you to understand since we're doing calculations with bits here. And I have to first convert this into a long. For some reason here, you can try writing 1L right shift n, but for some reason I tried that and the online compiler won't work with that, so I have to manually parse this 1 into a long and then use the right shift on that because we can get quite a big number. And so yeah, here everything smaller than this will have a length that is at most n, and the nth one will have a length of n plus 1. For example, here, as I said an example, and if n is equal to 4, then 1 right shift 4 will give us this. This is basically the same thing as at first you have this 1 as a bit, and every time you right shift, you basically add a 0 behind it. So here it will mean that as long as we're smaller than that, that means we'll go all the way from 0 to 1, 1, 1, 1. So this is what we want. We want to check each of those. And first, I will have to count how many ones we have in this number. So I converted this into a bit set. Here you must have a constant variable. So I set this to 32 because we know that the maximum length is 31. And I just added a few just in case. And this will count how many of the ones that we have. As long as the number of ones we have is less than or equal to L, we will do the following. We cannot just loop through all of this because the maximum can be 2 to the power of 31, and that's going to give you more than 2 billion, and using that and in a just linear loop, it will just take too long. So we have to compare these, and we can skip a few cases. So first of all, we know that this is smaller if the number of ones is less than or equal to L, then this is definitely a possible solution. We will increase count by 1. And we have to check if count is already equal to I, then that means we found our answer, and we will set answer to just I and stop the loop. Otherwise, we will use the following to skip the unnecessary ones. First, I set this other C variable to 0, and I counted how many of the last few, how many of the ending numbers are 1. So they have to be continuous starting at the end, and I'll count the last few ones. For example, this number 01011 will have, after we go through this loop, C will be equal to 2. And for example here, although there are ones, but none of them, there are no ones at the end, so the C will return 0. And then here we can, this is the part where we skip a few count and I. So we have to first check if we increase, so because there are a few of the numbers that we can skip, so we know the digits that we can skip. For example, here we can skip 2 digits. We don't have to loop through other 2 digits from this. So we will increase it by the power of 2 because we know that each of the digits can be set to either 0 or 1, and they are C digits. So using combinatorics, the amount of possibilities will be 2 to the power of C. And so we first have to check if that's less than or equal to I, because we don't want to exceed what we are wanted. And so if it's smaller than that, then we will increase I by this much, so we can skip those few numbers. For example, here, as I said, this will turn into this. So here, when we increase another 1 at the end, there are a bunch more, you can have a bunch of options here at these 3 numbers. For example, you can have 0 1 0 0 0, you can have 0 1 0 0 1, and you can have 0 1 1 1 0, for example. And there are a bunch of more for these ones, but we know that if the count is less than I, and we have to, and since we know that the length is also the number of bits that are 1 is also less than or equal to L, we know that these possibilities are definitely, we can definitely find any possible numbers in these 3 digits, so we can just skip those ones and just add it into our count right away. And so this is what this does. I have to minus this by 1 because this is a for loop, and every time we finish this round, I will also increase by 1. So if you don't minus this by 1 first, then I will just increase by 1 in the next round, and we're going to skip this number. And so just in case, if that number is actually a number that we're looking for, we don't want to miss that, so we have to minus this by 1, and also minus count by 1, because we took one less number. And then this else statement is if our amount of bits that are 1 is already greater than L, then we will skip everything that are after this. So this is the same thing as here, but now instead of counting how many ending 1s we have, we count how many ending 0s we have. And so here we will also skip this by that much, because, for example, here if you have 1 1 1 0 0 0, and you already, and our L is 2, then here we already have 3 bits that are 1. Then we know that definitely anything after this, for example, 1 1 1 0 0 1, 1 1 1 0 1 0, or 1 1 1 1 1 1, these ones will definitely not be possible. So we can skip anything for these last few 0 digits. And so this is why we also skip by 2 to the power of this much. And remember, here might seem complicated why we're using 2 to the power of something, but just think of it as a right shift. For example, if C is equal to 3, then we will skip 1000. Well, actually 1000. Can't really say it's 1000 since it's in binary form. And yeah, so that will help us skip all of these extra unnecessary zeros. Also, remember to minus this by 1 as well, since, as I said, this is a for loop and I will always increase. And so we'll just keep on going until we've reached a count that is equal to I. And since we're increasing count by skipping a few of the possible digits, we will shorten the compiling time of this code for a quite big amount. And at the end, we will get the binary version of our decimal answer. At first, the answer is in decimal base, so you have to convert it to binary base. You can use this bit set data structure. So then also set the maximum length to 32, so you don't have any overflow or anything. And if you just print this out, then you're gonna get 32 numbers. But most of the time we don't have n equal to 31, and so we only want to print out the n digits. And so just use this loop to print out each of the n digits that we're looking for. And finally, at the end, we just print out a new line to stop this program.